morning, everyone. My name is Allison Wing. I'm an assistant professor at Florida State University, and most of you don't know me because I do not study exoplanets or planetary atmospheres. I study tropical convection on Earth, but I was really excited to be invited by Ray to come here and speak to you about some recent work on something called Convective Self-Aggregation that hopefully you'll be really interested to hear about, and I'll be really interested to talk to you guys afterwards to hear what you think about how this might be happening or could happen on exoplanet atmospheres. So the kind of background for this is that in Earth's atmosphere, convection organizes on a variety of spatial and temporal scales. So it's not just scattered about, but it's often clumped together in some way. And so it's organized on fairly small scales, like in the order of 100 kilometers or so, in things like squall lines, groups of thunderstorms in a line. Things called mesoscale convective systems, like this one shown here, that's over India. But convection is also organized on larger scales, around 1,000 kilometer scales, in features like tropical cyclones, hurricanes, and typhoons, or equatorial waves. So this is just this band of convection propagating off of Africa here as an easterly wave, for example. And then we even have convection that's organized on the planetary scale. So there's something called the Madden-Julian oscillation, which is a thousands of scale blob of clouds and convection that slowly moves from the Indian Ocean across the Pacific Ocean with a time scale of 30 to 60 days. It's also called the intraseasonal oscillation. So this organization of convection is really ubiquitous. And all of these sorts of types of organization can be caused by a variety of different mechanisms. And so convection can be organized by vertical wind shear. So this is when winds change with altitude. That's something that helps those squall lines organize, for example. Convection can be organized by sea surface temperature gradients, where the clouds in convection tend to occur where we have our warmer sea surface temperatures compared to the cold regions, as well as by dynamical disturbance. So things that arise out of instabilities in the dynamical flow itself. So those are some ways that convection can organize, but today I'm going to talk about something different. I'm going to talk about a particular type of convective organization called self-aggregation. But before I get into explaining what self-aggregation is, I want to just give you some background on atmospheric convection more generally, because I know that we have a bit of a mixed audience here. So to talk about convection, I actually want to take it even further step back and talk about radiation, which I know that many of you know quite a lot about. So thinking about the situation on Earth, what does it look like if we only have radiative processes going on? Where we have shortwave radiation from the sun that heats the surface of the Earth and the atmosphere. And then the surface and the atmosphere then cool by emitting longwave radiation. And if this is the only thing that goes on, the planet will get into a state of radiative equilibrium, which is the equilibrium state of the combined atmosphere surface system in the absence of non-radiative fluxes. And so what the act of radiative heating does is to try to drive the actual state towards this state of radiative equilibrium. And this has several important properties. Its properties, of course, depend on the composition of the atmosphere. So when we model this, we have to put in the particular trace gas profiles that your planet has. And one important thing is the non-local effects of radiation. So changes in one layer affect others, and that turns out to be important later on for this convective organization. So you can, of course, do a radiative transfer calculation to calculate the profile of temperature you would get if you put in the particular parameters for Earth or any other planet you're interested. And so this was first done many, many decades ago for Earth, and this is just an example of a one-dimensional radiative model from Anabi and Strickler, and it shows the temperature profile that you would get. And so there's several features here that are, more or less correct for Earth. We have temperature that decreases with height in the layer close to the surface. And then after reaching a cold point, it turns around and increases in the stratosphere. And this is because the composition changes here. We have heating from ozone that causes this temperature increase in the stratosphere. But this is not quite exactly what the temperature profile on Earth looks like. So what's wrong with this? Well, first of all, the surface is way too hot. It's not 340 Kelvin on the surface of the Earth, at least not yet. The tropopause temperature here is also way too cold. It should be closer to 200 or 220 Kelvin. And the difference in temperature, the lapse rate, how temperature decreases with height, is too large. It falls off much too quickly. So what is missing? Why is this not right? Why does this not reflect what things actually look like on Earth? Well, what's missing is convection. So it turns out that this lapse rate that we have in the troposphere is one that is very unstable to convection, okay? So a parcel of air that rises in the atmosphere would cool less than what this environment would be doing, and therefore would be continue to accelerate and convect. However, the stratospheric profile looks pretty decent. And so actually radiative equilibrium works pretty well for the stratosphere, but in the troposphere, this layer where weather occurs close to the surface, we need to consider convection. So we go back to our little schematic here. This is unstable, and so it's not realized in Earth atmosphere, and we begin to have overturning and convection occur, where we have then turbulent fluxes of sensible heat that transport heat in the vertical. And so here I'll call this radiative-dry convective equilibrium, because we haven't talked about moisture yet. And what that is then is a statistical equilibrium between the net radiative cooling of the atmosphere and these turbulent fluxes of heat. Okay, so we can, take that into account into our model and model a state of radiative-dry convective equilibrium. And this is what we get, the second line here, where we allow it to convect to a neutral state for dry convection, which is called the dry adiabatic lapse rate. So this looks better than it did before, but there's still some problems. The surface of the Earth is still a bit too hot. It's like 320 Kelvin or so. That's still too warm. Our tropopause is still too cold, and our lapse rate is still a bit too large. So again, in dry RCE, radiative convective equilibrium, the lapse rate is minus 10 Kelvin per kilometer, but in reality, we know from measurements that temperatures fall off with height at around a rate of 6.5 Kelvin per kilometer. So we're still missing something here, and what we're missing is the fact that we need to consider moist convection in Earth's atmosphere. And this is because above a very thin boundary layer near the surface, most atmospheric convection involves a phase change of water. And so if we imagine a parcel of air that is rising in the atmosphere, as it rises, it cools, and at some point it reaches its saturation vapor pressure, and then condensation occurs, and you have a cloud forming. And once it's saturated, it then rises at a different rate, because as you have the condensation and cloud formation here, you're releasing latent heat, and so that adds some heat back into the system, and you don't therefore cool as quickly as if you were dry. So the picture we have in the end is this state of radiative-convective equilibrium, where again, it's a statistical equilibrium between the net rate of cooling and turbulent fluxes of heat, but now we have to consider latent heat as well, evaporation and condensation heating, and we have transport of heat in the vertical by these rising air parcels, warm air parcels in clouds. So that's radiative convective equilibrium. And so this is how I think about how convection arises in the Earth's atmosphere. It's because our radiative equilibrium state is unstable, and so therefore it convects. And we have in the tropical atmosphere this occurring, everywhere basically. So what are the consequences of the fact that we have this moist convection occurring in the atmosphere? Well, if we take our sort of one-dimensional model then and now put it in the case of moist convection, we get this profile here. And this, as I mentioned, is representing temperature that's decreasing not quite as strongly with height. And this is because, again, the significant heating due to the phase change of water reduces the temperature lapse rate. You don't cool as much as you're lifting up. And so this allows the atmosphere to convect to a more stable lapse rate than if we didn't have moisture involved. The fact that we have moist convection also cools the surface a bit. So now we're at a realistic value of around 300 Kelvin for our average surface temperature. So that's an important feature as well. There's several other consequences of the fact that the convection that happens is moist, involves the phase changes in water. One is that it redistributes water vapor, which is an important greenhouse gas in the atmosphere. So that has radiative consequences. And if this was the only thing that moist convection did, it would still be very important for us to consider. But it's not the only thing it does. It forms clouds, which themselves affect the albedo and long wave trapping and have huge radiative impacts. Another sort of unique feature of moist convection is that it causes us to have widely spaced updrafts. So this is just a picture from an airplane of some tropical convection. And you can see that we have rising motions in these clouds here, and then it's sort of there's these large areas of clear air, which is sinking in between. And this is because the air that is sinking in those clear sky areas, the rate at which it sinks is controlled by how strongly the atmosphere is cooling in those regions. And that is not a very, very fast rate. So it sinks pretty slowly, whereas in clouds, the air rises pretty quickly. And so if we have air that goes up quickly but down slowly, we need to have a fractional area difference in the coverage of those areas to have mass balance. So the air that has to go up in pretty narrow regions, and the air that's going down has to cover large areas to balance. And so this is a really sort of fundamental property of moist convection that is not the case for dry convection. In dry convection, you can have symmetry between your up and down motions. So keeping all of this in mind, then what are the properties of our state if we consider the atmosphere to be in the state of radiative-convective equilibrium, or RCE? Well, again, we have this balance between net radiative cooling and the turbulent fluxes of heat. One important thing to remember is that in this way of thinking about it, convection is a mixing process. It's not some externalized heat source that just pumps heat into your system. No, it moves around heat in the vertical. And so you cannot just assume it as some sort of import of heat into your system. And it arranges itself to balance the radiation. So here, the radiative cooling is being driven by external things like the sun and the constituents of the atmosphere, and convection just does what it needs to in order to balance that radiative cooling. You have this battle between convection, which is trying to make things neutral to convection, and radiation, which is trying to push you towards radiative equilibrium, which is very unstable. And in that battle, convection wins, because convection is a fast process, whereas radiation is slow. I mean, the radiative relaxation timescale in Earth's atmosphere is on the order of a month or so, whereas the convective timescale is like an hour, okay? So that's why our mean temperature profiles in this balanced state are the ones that are corresponding to a neutral state for convection. And this has important constraints then on the basic properties of the climate system. It constrains our lapse rate, that decrease in temperature with altitude, to be moist adiabatic, which has other consequences for how things depend on warming. So for example, that rate changes with warming because, again, the moist convective lapse rate changes with warming. And it causes, if we're thinking about future climate change, for example, it causes the upper troposphere, temperatures at 15, 20 Kelvin in the tropics to warm more than they do near the surface. Now, this again is a statistical equilibrium. It holds on average over a large area and time scale. It doesn't hold at any given particular location. And it's upset by large scale circulation. So if you have lateral transport of energy in the horizontal, then you don't necessarily have this holding. But if you integrate over those circulations, it works on average. In addition, one really fundamental property is that in this system, the radiation and the convection are highly interactive, okay? Because radiation, the radiative cooling rates depend on water vapor and clouds, and convection controls the distribution of water vapor and clouds. And so this interaction between the two gives us the potential for instability. And that's what I'm going to talk kind of in the rest of the talk about. So we can simulate this sort of state in a variety of different modeling frameworks. And there's been a long history of doing this, starting with these sort of one-dimensional simulations I talked about in the 1960s. But then moving on to two-dimensional simulations where you're actually explicitly resolving the clouds and convection and convective heat transports. And then more recently in three-dimensional simulations. And so in a three-dimensional simulation, how do you simulate RCE? Well, you consider usually some sort of doubly periodic box that's hundreds of kilometers in each dimension and, covers the depth of the troposphere plus a bit more. At the top of the model, we have solar insolation coming in, and we constrain that to be the same everywhere across the domain. So there's no gradients in the solar insolation. And the lower boundary condition is also homogeneous. Generally, it's fixed sea surface temperature, and we make that the same value everywhere. So everything is the same everywhere across the domain in terms of the boundary conditions enforcing. And we just initialize it with random noise in the boundary layer just to kind of get things moving. And it begins to convect and overturn. And then those clouds and convection are resolved explicitly by, the governing equations in this model, which are, the basic fundamental dynamical equations of motion. And we can see what state it ends up in. So the best way to show you that is to actually just show you. So this is a movie of one of these cloud resolving simulations of radiative-convective equilibrium. We're looking down here on the model. It's about 1,000 kilometers in each dimension. The gray shading are clouds. So it's basically one isosurface of cloud condensate. The red colors, the color shading is humidity near the surface, where red is kind of moist air and blue, as you can see developing here, is dry. So initially, as you can see, the clouds and convection were kind of randomly distributed. It looked like popcorn or fireworks or something like that. But that doesn't stay that case. In particular, we see this area of drier air that starts to form, and we don't have clouds and convection there anymore because thunderstorms don't like it when there's dry air. And this dry patch gets drier and drier with time, and it starts to expand. And so this is what is leading to this self-aggregation process. As that happens, the moist areas of the domain get moister, whereas the dry areas get drier. And so you have this net sort of transport of moist static energy and moisture from the dry regions to the moist regions. And as the dry region expands, convection is suppressed there and therefore becomes increasingly localized into a single, or in other models, perhaps multiple, intensely precipitating cluster. So all the clouds and precipitation and rising motion is confined in this one area, and the rest of the domain has drier air that is clear and slowly sinking. And so this is known as self-aggregation. It's this spontaneous transition from randomly distributed to organized convection. So there's nothing that said, oh, I need to have my clouds here. All the conditions were the same everywhere. It decided to do that on its own. And what causes it to do that? Well, I'm going to explain this in more detail, but it results from interactions between the convection and its environment involving clouds, water vapor, radiation, surface fluxes, and the circulation. This localization of convection was first seen in a paper by Isaac Held in 1993. And I'm going to attempt in the rest of my talk to summarize a couple recent reviews that I wrote on the topic. Okay, so let's try to better understand what this self-aggregation phenomena is, what causes it, and what impact does it have? I mean, does it matter that the convection is organized in a clump like this? I mean, if you're in this spot and it's raining on you, it matters, but does it matter for the larger scale climate of the atmosphere? And the first thing I'd like to say is that this is not a peculiarity of just this one particular model or this one particular simulation. This occurs in a wide variety of models and model configurations. So it was first seen in two-dimensional cloud resolving models, this Held paper I mentioned. So this is just showing an image from that paper. This is the spatial axis of the model, and then these are time going forward. The shading here is precipitation, rainfall. And so you see initially it's sort of scattered about, but then it gets organized into these two kind of clumps that stay in the same place as time progresses and eventually collapses only to one. That's 2 dimensions. What about 3? Well, I just showed you a 3-dimensional movie, but just to show a couple other examples. This has been found to occur in a lot of different small domain, square, 3-dimensional cloud resolving models. This was the first one, Tompkins and Craig 98. We're looking just at the left panel here. What's plotted is a measure of humidity. And so you see these kind of alternating moist and dry regions. This was a really seminal paper on the topic by Chris Bretherton et al. In 2005, where again, you have all of your precipitation confined in this one really strongly raining cluster that is very moist, where the rest of the air surrounding it is dry and clear and cooling very strongly to space. We also have seen it to occur in 3-dimensional models of other geometries, including ones that are long channels, kind of like a bowling alley. So this is an example from one of my papers. This domain is 3-dimensional, but in the horizontal, it's 12,000 kilometers long. So that's, substantial part of the way around the world, but only 200 kilometers wide. And what's shown here on the top is clouds and precipitation, and the bottom is moisture. And so again, you can see you have kind of an area of clouds and precipitation, and then a dry area, and then another clump, and then a dry area, and so on and so forth. And again, here the boundary conditions and everything are exactly the same everywhere, yet it does this on its own. We have also found that self-aggregation occurs in regional and global models that have parametrized convection, so that are running at a coarser spatial resolution, so they have to parameterize convective motions and condensation and cloud formation. This is an example of a couple different GCMs, and these are the same models that are used for climate projections, CMIP5, that sort of thing. But they're run here in this state where there's no land, there's no meridional insolation gradients, there's no sea surface temperature gradients, yet they still have this clustering of the precipitation into clumps around the world. And then more recently, we've also started to been able, with computing advances, to do full global simulations, but with models that explicitly resolve convection. And so this is an example from the Japanese NICAM group of a global simulation. I think this was around 10 kilometers. And again, you see clumps of precipitation forming. Now, all of these simulations that I talked about, this was in a configuration with no rotation. So we stopped the Earth from spinning and it's just sitting there. And so that's sort of representative of what things would be like near the equator, because the Coriolis force is 0 at the equator. But if we turn rotation back on and do rotating RCE on, for example, an F-plane, then we get a hurricane to form. So the convection still self-aggregates, it just does so into a spinning cluster instead of a singular one. And if you give it a high rotation rate, you just have a world that fills with tropical cyclones, which is pretty cool to watch, actually. Okay, so that's sort of what self-aggregation looks like. But how can we describe it more quantitatively? Well, as I was telling you when we watched that movie, as self-aggregation progresses, we have this moistening of the moist regions and drying of the dry regions. So we have a broadening of our humidity distribution. One way to measure that is by something called the moist static energy or frozen moist static energy variance. And this is just a particular variable that depends on moisture in the atmosphere, but it's an energetic quantity. And so we like to use it because it's something that's conserved in the atmosphere. So we always like to have conserved quantities. They're easier to track. In particular, this is the equation here. So it depends on the sum of internal and potential energy and then latent energy here, including some contributions from ice. That's why it's called frozen moist static energy. And the important thing is that if we take the column integral of this, integrated over the whole depth of the atmosphere, that column integral is not changed by convection. Convection just redistributes moist static energy in the vertical. So when we do a budget for this quantity, it's easier because we don't have to deal with convective tendencies, which can be difficult to measure. Now, in the tropical atmosphere, most of the spatial variability in this quantity comes from the moisture term. So this reflects this moist regions getting moister, dry regions getting drier that I talked about. So this is, the axes on my plot disappeared, but this is time from the beginning of the simulation to the end, and then the variance is increasing here. It's on a log scale, so each of these kind of larger ticks is an order of magnitude. And these are all just a couple sets of simulations. And so we can see that in all of them, the moist static energy variance increases rapidly in the simulation. So this is reflecting these moist regions getting moister, dry regions getting drier. And it increases about 2 orders of magnitude. So this is a big change. Okay. Now, since we have this quantity that increases as the convection aggregates, that means that a process that is acting to increase that variance is a process that favors this self-aggregation. Okay, so this is kind of begging for us to actually do a budget for this quantity, and that can tell us what mechanisms are leading to the self-aggregation in these cases. And so if we do a budget for this spatial variance of this moist static energy quantity, this is what we get. And basically the important thing here is that so here's the tendency of the variance on the left-hand side. And each of the terms on the right-hand side has to do with a source or sink of moist static energy. So what are those? Well, first we have our turbulent fluxes of moist enthalpy from the sea surface to the atmosphere. This is things like evaporation and sensible heat flux. We then have our shortwave component. So this is the column shortwave flux convergence, so the difference between the shortwave radiative fluxes at the top of atmosphere and the surface. Then we have the same for the long wave, again, difference between top of atmosphere and surface. And then we have a term having to do with advection. So this is lateral transport of moist static energy in or out of our column. And so each of the terms in this budget is a feedback term where we have the product of an anomaly in moist static energy itself, this H prime, and an anomaly in one of these sources or sinks. So if we have a process that is acting to increase the moist static energy of an already moist region, let's say we have more evaporation where we already have lots of clouds and moisture, then that's going to act to increase that moisture anomaly and cause a positive tendency in this variance. And so therefore we call that a positive feedback and say that it favors self-aggregation. However, if we have a process that is acting to decrease the moist static energy of a moist region, then that would damp that anomaly, and we say that that would act against self-aggregation as a negative feedback. So we can calculate this budget in our model simulations and integrate it over the whole domain and say, okay, what processes are contributing to this increase in moist static energy variance? What processes are leading to self-aggregation? And so we can do that here. And again, the x-axis here is time in our simulation. Above the dashed line is positive, below is negative, and just focus kind of at the beginning of the simulation because we're interested in this initial sort of instigation of aggregation. And so each of the lines is one of the terms in our budget. And really the key thing to take away is that at the beginning of the process, out of the colored lines, it's the blue and the green one that are positive and strongest. And so that's the long wave and surface flux feedbacks. And so we say that those are the processes that are driving the initial development of aggregation. So what does that mean? What physically are these feedbacks representing? How can we have them be positive? So first, let me talk about the long wave feedback. How do we get a positive long wave radiation feedback in this context? Remember, this is the feedback on these sort of spatial gradients, of feedback on the self-aggregation. Well, if we think about some parts of the atmosphere that are a bit moister than other parts that are dry, we have preferentially our clouds and convection occurring in the moist regions. So we have more clouds or water vapor in the moist regions than we do in the dry regions. And so that means that the atmosphere in the dry regions, there might be some shallow clouds or something. The atmosphere there is cooling very strongly, okay? Because a lot of the radiation emitted from the surface and these low clouds can readily escape to space because it's very relatively transparent to radiation when it's very dry. So dry regions are cooling very strongly. Whereas in the moist regions, we have trapping of that long wave radiation by the local greenhouse effect from all of the clouds and humidity there. And so the atmosphere itself in these moist regions is cooling much less. So we have small cooling in the moist regions, large cooling in the dry regions. And this will act to amplify those existing anomalies, because where we have large amounts of cooling, we're going to cause more subsidence, which is going to dry the atmosphere even more, make it more unfavorable to convection, and cause a further decrease in moist static energy. Whereas in these moist regions where it's not cooling very much, that means it's going to be favorable for convection to continue to occur there. And so this is a positive feedback because we're amplifying the existing pattern. Okay? And it has to do with the fact that convection is controlling the distribution of clouds and moisture, but then that affects the radiative tendencies in a way that positively feeds back on the convection. Now, I'll just say that this doesn't always have to be a positive feedback. Whether or not it actually is depends on the vertical structure of your humidity perturbations and what your kind of basic state was. But when it turns out to be positive, this is why. So that's the long wave radiation feedback. I also mentioned that the surface flux feedback was contributing to self-aggregation. So what does that mean? What is a positive surface flux feedback? Well, here we're talking about surface enthalpy fluxes. So these are, again, these turbulent fluxes of latent and sensible heat from the sea surface to the atmosphere. So if we again consider our little schematic where we have more clouds and convection in the moist areas than in the dry, when we have more convection happening, we have stronger winds at the surface of the atmosphere. Because, you know that you've experienced this when a thunderstorm rolls through, you have these strong gusts of wind and it's very turbulent for a while. Whereas in the dry regions where we don't have a lot of convection going on, it's pretty quiet and the winds are not very strong. So more winds, more gustiness in the moist convecting regions than in the dry. And it turns out that enthalpy fluxes at the surface depend on wind speed, okay? This is called WISHY, the wind-induced surface heat exchange effect. And you know this if, like this morning, after I showered, my hair was wet and I walked outside, and as the air blew on it, I was like, oh gosh, I feel very cold because all this heat is evaporating from my head as the wind blows. So that's why we use hair dryers. transfers the evaporation of the water on our hair more efficiently. So where we have stronger winds, we have more evaporation, stronger flux of heat from the sea surface to the atmosphere. And so we've got large surface fluxes where it's moist, small where it's dry. Now, there's other things that can affect this. These fluxes also depend on the enthalpy disequilibrium, the difference in temperatures and humidity between the surface and atmosphere. But at least in the beginning, this wind effect wins, basically. And so we have more evaporation in the areas where it's already moist, and so we're going to moisten those. So this is, again, a positive feedback on aggregation. Now, these are not the only two processes that can contribute to aggregation. They're kind of the most important ones, but there are a couple other things that can happen. So just to kind of summarize all of the processes that favor this self-aggregation clumping of convection. Well, again, we have our radiative feedbacks, the long wave feedbacks, which have contributions from just water vapor as well as clouds. So we've got long wave water vapor and long wave cloud feedback, which work pretty much the same way. We have our surface flux feedback that, again, is driven by this wind speed variability. But these radiative fluxes have more than just a direct impact on the cooling in their column. Whenever you have spatial differences in the amount of radiative cooling, that can also drive lateral circulations, okay? A heating difference drives motion. So we can also have a coupling between cooling, particularly the strong cooling at the top of low clouds, and a circulation. And I'll explain more in a moment what that means. And then we can also have contributions from the feedback between moisture and convection. And so I was sort of alluding to this when I was saying, well, convection likes to occur where it's moist, and where you have convection, it moistens the atmosphere even more. And so kind of convection begets more convection in that sense. But just to kind of explain this radiative cooling circulation coupling a little bit more, here's a kind of more detailed schematic of it. The idea is, again, you have your deep convection in clouds in one area, and then this drier area where maybe you just have some shallow clouds outside. And basically, in the dry region, we have this large-scale sinking air, large-scale subsidence in the atmosphere. That promotes the formation of these low clouds, and those low clouds cool very strongly at their tops. Okay, so that's represented here by these little purple squiggles. This low-level cooling drives a shallow circulation that increases the subsidence in these areas, right? Because if our air is cooling, it needs to sink in order to balance that temperature change. And so as it sinks, then it has to spread out, and then will rise back up in the convecting areas. And so these are called radiatively driven cold pools. And because of the spatial differences in the cooling, we get these circulations that form that will act to kind of give convection an extra boost in those areas where it's already occurring, and continue to damp it where it's not. And so these effects of the convection on the radiation have both direct effects locally and indirect effects because of how they can drive circulations. Okay. So that's why this convection can organize. Again, it all depends on how the clouds and water vapor that are affected by the distribution of convection, how they interact with circulations and these radiative fluxes. And so it's this, because it's the interaction with convection and its own environment, that's why it's this self-aggregation we call. So earlier I said, we want to know, does this matter? Like, why do we care that clouds are clumped together? Well, it turns out that self-aggregation is not just a spatial reorganization of convection, but it has a large impact on the domain mean or large-scale climate. Okay, so it has a kind of more fundamental effect on things. So what is that effect? What is different about the average state of that simulation when the convection is clumped together versus distributed randomly? Well, the first one we've already talked about. Dry regions get drier and moist regions get moister. Another way to view this is by looking at the spatial variance of humidity itself. So this is column relative humidity, which again, in these simulations that start out from a random state, as they organize and the convection aggregates, we see a big increase in the spatial variance. And that occurs, these are all simulations at different temperatures, and it occurs in all of them. Okay. So dry regions get drier, moist regions get moister. As the dry regions get drier, that means you're opening up more of these clear sky radiations that can cool more strongly to space. Now, this is showing a column integrated measure, but if we look at profiles of humidity, it turns out that dry regions get drier at all levels, okay? And there's a lot of lines on this plot, but the key thing is that the blue lines are measuring the profiles of humidity. This is specific humidity as a function of pressure, so the surface is down here. The blue ones are profiles of humidity in the moist regions, and the red are in the dry regions. And as we go from the kind of dark colors, that's with time in the simulation. So as we go along with time, the moist regions get moister and the dry regions get drier. And as you can see, that occurs at pretty much every level, including, pretty close to the surface. The strongest change, though, is in kind of the lower to mid troposphere. If you look at this drying, I mean, this is a big difference, almost in some cases, a factor of 2 or more. This one simulation in the dotted line is a particularly extreme one where you lose almost all of the water vapor in these dry regions. And so that, has a really big impact. Okay, so this is reflecting this broadening of our distribution of humidity, more moist and dryness. But what about the mean state at all? Is the average drier or moister than it was initially? Well, you can kind of figure out the answer. If I said the dry regions are getting drier, and we saw from those movies that the dry areas cover a larger fraction of the domain, it turns out that the mean state is drier. And this we see in these simulations of self-aggregation, as well as in observations of aggregated convection. And so in observations, we can't say what specifically was causing the convection to organize, but if it is organized, we also note that the average atmosphere around it is drier. So here the black line is the simulation, the red is observations, dashed is when the convection is scattered, and then the solid line is when it's organized. And here it's, in this case, relative humidity that's plotted again in the lower to mid troposphere. We see this big amount of drying as we go towards more aggregated conditions. It's less extreme in observations, but we still see a signal of the same sign. Okay. So we've got drying in the dry regions, drying of the mean state, and that's shown here on the right again. But what about temperature changes? Well, it seems that we also see a warming of the atmosphere when convection aggregates. So here, these plots are showing differences between the end of the simulation when it's organized and the beginning when it's not. And so if it's positive, that means that when it is organized, it is warmer. So here the sign is positive on the right. And then again, drier when we are aggregated. And again, my axis was cut off, but this is a difference of a couple degrees Kelvin. So that's significant, actually. And it has to do from the fact that when convection is clustered together, you have your air parcels that are rising in your clouds rising in moisture regions. And so they're less susceptible to entrainment because so you have less mixing and they lose less buoyancy as they rise. And so you're able to convect to a warmer temperature. So we've got drying in the dry regions, drying of the mean state, and warming. All right, so that's already some substantial changes. Is there anything else going on? Well, there's also a change in the distribution of clouds. And in particular, on average, there's a decrease in the amount of high clouds with aggregation. And I show this a couple different ways here. These are, again, differences between the end of the simulation when things are clumped together and the beginning when they are more scattered. And on the left, this left panel is showing the actual cloud fraction, so the fraction of the domain at any given level, height that is covered by cloud. And we've got 8 different simulations on here, so it's a little bit messy, but you can kind of see that you have this that's negative basically in all of these. You have a decrease in the amount of high cloud, which you can see maybe a little bit better in this panel on the right, which is showing the actual amount of cloud water. This is ice cloud, solid phase condensate here, which is all decreasing at these high levels. In terms of low level clouds, we see some increases in the amount of low cloud with aggregation, but then there's some simulations that seem to have a decrease. So it's a little bit less clear, and shallow clouds in the atmosphere occur on kind of small scales, and so you need really high resolution to do them properly in models, and these simulations don't have super high resolution. It's about 3 kilometers, so I wouldn't really trust the low clouds, but the deep clouds are pretty good. And so we see this pretty robust, and this is seen across many, many models, big decrease in the amount of high cloud that we have with aggregation. So when we're clustered, we're warmer, we're drier, we're especially drier in the dry regions, and we have fewer clouds. So we've changed the temperature, the humidity, and the cloudiness. And these are all things that are really important for the radiative energy budget, okay? So those changes have big consequences for the energy budget of our climate, in this case, when the convection is more clustered together. So with aggregation, as the convection is more clustered, we have an increase in the outgoing long-wave radiation. So this is, again, these are all plots of time evolving in the simulation. So as time goes on, things get more clustered. So we've got more radiation escaping to space from the top of the atmosphere. And because we kind of have these opposing changes in clouds, less high clouds, but more low clouds, the reflected short radiation doesn't really change much. And so our net top of atmosphere flux is also reduced in magnitude. So we have less flux into the top of the atmosphere. So overall, we're cooling more. Okay, there's more energy being lost to space when we're aggregated. That's reflected as well by an increase in the tropospheric rate of cooling. So this is the column rate of cooling. So this is the difference in fluxes from the top of the atmosphere to the surface, or equivalently, the vertical integral of the radiative cooling. And it's more negative when we have convection clustered. So again, we're cooling more when the convection is clustered together. And that's because when it's all clumped together, we've opened up these huge areas that are dry and clear and can radiate very strongly to space. The big, radiator fins, as Ray put it in one of his seminal papers, of the atmosphere. In addition, we have some changes to the surface energy budget. We have a decrease in the energy gained by the surface. And because it's generally windier when convection is clustered, we have an increase in surface enthalpy fluxes. Now, since a lot of this is evaporation, we have to have water balance in the system. So if we have more evaporation, we also have to have more rainfall. And so we see an increase in mean precipitation. So these are all things that are really important for sort of setting the climate of our atmosphere, and how strongly it would respond to perturbation. So you can imagine, if we have a radiative forcing, like we're, say, increasing carbon dioxide or something, and the amount of clustering of convection changes, then all of these energy balances would change, and that would affect how sensitive our climate would be, potentially to a climate perturbation. And so this, has potentially big implications, which as a field, we're still trying to figure out. So just to summarize, self-aggregation warms and dries the mean state, reduces high clouds, enhances the dryness of dry regions, increases the ability of the atmosphere to cool the space. I didn't talk about this, but it might be temperature dependent. Again, still figuring that out. And so therefore it might be important for climate. So in the last minute or two, I just want to kind of conclude here by kind of reminding you that in radiative-convective equilibrium, this kind of idealized state of the tropical atmosphere, the organization of convection takes the form of this self-aggregation, which is this spontaneous clustering of convection in an otherwise homogeneous environment, where we go from scattered convection in the beginning towards clustered at the end. And that's driven by these feedbacks involving radiation and surface fluxes and how they interact with convection. So this has all been, simulations in this idealized world of radiative-convective equilibrium, where we have this nice statistical balance between the convective heating and the radiative cooling. And as I said, that works on average as a representation of our atmosphere, but at any individual spot, it doesn't hold. And the model's configuration that in these simulations I've been talking about is pretty different from how the real Earth looks. So a question that I get asked a lot and that I think about a lot is, how might self-aggregation manifest in the real world? Right? So in RCE, self-aggregation is the manifestation of these radiative-convective feedbacks, but RCE world looks pretty different than Earth, okay? On Earth, there's rotation, for one. There's gradients in temperature, right? It's warmer near the equator than it is at the pole. There's land. And there's all sorts of dynamical disturbances and other circulations caused by other things, mid-latitude weather systems, the Hadley circulation, Walker circulation, all that sort of stuff. So, there's a lot of other things that can control the distribution of convection in the real world and cause it to organize. And, is this meaningful, basically? Is self-aggregation actually happening in the real world? Well, we don't really truly know the answer to that, but what I think is that the same feedbacks, these radiative-convective surface flux feedbacks that cause self-aggregation in radiative-convective equilibrium, those same feedbacks may contribute on real Earth to help convection that's maybe initially organized by something else, help that stay organized or help it organize more quickly. I think that those same feedbacks can help tropical cyclones, which are one special type of convective organization, help them form and intensify. And so in particular, there's growing evidence that cloud radiative feedbacks specifically that are driving self-aggregation, those cloud radiative feedbacks might also be very important for hurricane and typhoon formation. And we already know they also affect other things about its structure. And it's also possible that these radiative convective feedbacks that give us self-aggregation, they, in the real world, when we're on a equatorial rotating beta plane, might give rise to the Madden-Julian oscillation, this planetary scale progression of a clump of convection from the Indian to Pacific Ocean. And so there's growing evidence that the MJO, which is pictured here, again, it's just this big blob of clouds, that the MJO is what's called a moisture mode that is destabilized by these cloud radiative feedbacks. And indeed, if you take a model that was initially RCE, that self-aggregated, and you stick it on a beta plane, so we have rotation that varies with latitude, then we get something that kind of looks like an MJO. So those are the areas where I think, this self-aggregation phenomena is playing out in the real atmosphere, as well as just kind of helping convection and clump together more generally. And a lot of my work now is, trying to make these convection connections stronger. So what I'd like to leave you with then is something for you guys to think about and maybe chat with me about at the break is, could this convective self-aggregation occur in exoplanet atmospheres? I mean, to me, it's super exciting because with exoplanets, there's such a huge diversity of possible planets and atmospheres out there. Maybe there's one where it looks like RCE, where it's an aquaplanet and it's so far away from the sun, you don't have, meridional insolation gradients and it rotates really slowly or something like that. In general, in order for this to happen, you need to have an atmosphere where you have convection happening in the atmosphere. So it needs to be unstable in a way to have convection. And that convection would need to occur in a way that it affects the distribution of a radiatively active condensable species. And it needs to do that in a way such that you have less radiative cooling where you would have the convection, which then invigorates it. So you guys have to tell me about what convection looks like and what the condensable species are and if its radiation behaves in that way. But I think that there's some exciting possibilities there. And hopefully this has been interesting for you to hear about and think about, maybe change the way you think about how convection behaves in atmospheres. So thank you very much for your attention. I'd be happy to take questions.
Just have to find the microphone.
So, I'm Dorian Abbott from University of Chicago. In the small scale, in the doubly periodic domains, it looked like mostly the convection aggregates at the domain scale. Mm-hmm. In the Radiative-Convective Equilibrium global simulations, there seemed to be a scale, and it looked like in the different models, the scale was different. Mm-hmm. What sets that scale?
That's a good question. We don't know the answer. Certainly in these, as you mentioned, in these sort of square things, it seems to scale with the domain size. So people have finally figured out, if you get up to 10,000 kilometers, then finally you start getting multiple clusters. So there does seem to be some natural limiting length scale to the size of these clusters. It is on the order of a couple thousand kilometers, like order 1,000 kilometers, we would say. But as for what physically sets that, we don't know. I had a theory sort of involving boundary layer remoistening lengths, but it kind of worked, it kind of didn't, so I don't really believe it. People are still working on it. But it's tricky. It's a tricky problem because in a non-rotating state, we lose a lot of our natural length scales in the atmosphere. There's no Rossby deformation radius or things like that. There's maybe some length scales involving, frictional dissipation or something like that. So we're still trying to figure it out. But, I think it's, if it's set by some, fundamental property, all these models are, having different treatments of boundary layer representations, convection, et cetera. So I think it's reasonable that they would do that, give it a different length. But that's an open area of research.
We have a question.
Hi, Ralph Lorenz, Applied Physics Lab. A really interesting perspective, and I'm eager to sort of see this applied to solar system atmospheres as well as exoplanets. And I'm grateful to Dorian for asking about the length scale and periodicity, because I had the same question. The other question I had was with respect to the long wave feedback, where the slide said subsidence causes low level cloud. And I wasn't sure how that worked. Is that just subsidence causes cloud to occur at a lower level than it would otherwise do? Or, I mean, how does subsidence cause condensation? That's sort of counterintuitive.
Well, so it's more that it's affecting sort of the profile of cooling and heating in the atmosphere. So you would have any convection that would happen would be capped and couldn't get any higher. And in the real tropical atmosphere, we generally see in subsidence regions, in the low levels, you have a trade inversion. And so below that, the air is unstable, and you can have right at the top of that layer cloud formation, but it can't go any higher. And so having subsidence actually helps keep it kind of confined to that layer. And then again, the strong cooling that you have at the top of that layer, that helps maintain the convection. You can get convection if you're heating from below or cooling from above. And so both of those are contributing to the low clouds there.
One more question on the back, then we go back to the front.
Yeah, Eric Gaidos, University of Hawaii. So my question is a segue to Dorian's, which is basically, these simulations are idealized in terms of their surface by necessity, but have people looked at, or you looked at, the fragility of the process to an imposed physical structure? The real Earth has lakes, mountain ranges, forests, lots of
heterogeneities. Yes.
Right, and do those play into basically setting, for example, the length scale of this aggregation? This is something that might distinguish, for example, an aquaplanet from a planet which has no such smooth surface.
Yeah, so if you put in surface heterogeneities, that kind of tends to tell the convection where to cluster. So for example, if we put in something kind of like an island in these simulations, you'll have a cluster over the island, but then you might have other convective aggregated clusters elsewhere as well. People have done simulations also with interactive surface temperatures, which can cause some interesting kind of internal variability in the structure of the aggregation. But yeah, I guess basically any heterogeneity is going to probably be a stronger influence on telling the convection specifically where to organize than this random kind of self-aggregation process. And so that's why, it's sort of, you have to kind of think a lot about how this is happening in the real world. There are places in the tropical ocean where there are relatively weak sea surface temperature gradients, but in, kind of land areas and things like that, those are probably stronger influences. If, for example, you put in a sea surface temperature, like a Mach Walker kind of circulation type thing, again, the convection kind of chooses to be over the warm areas, but these sort of feedbacks can still be going on to amplify the organization that evolves.
So 2 more quick questions.
My question just actually got addressed.
Okay, so Nick.
Why does self-aggregation saturate? Like, what negative feedback kicks in at the end that makes it flatten?
Oh, that makes it stop?
Yeah.
Well, you have to have some amount of convection happening, right? Because we have cooling happening. So we have to have convection to balance that. So you can't have the cluster, collapse into a pinpoint and go to zero. And so in terms of what scale takes to do that, that goes back to the question that Dorian asked about the length scale. Why do we stop, seeing an increase in the variance and the drying of the dry regions? It is adjusting to a new equilibrium, basically. And once it gets into a state where it can rebalance things out and have this energy balance, then it's happy and then it stays there. And one thing I didn't mention is that once it aggregates, it stays that way as long as you run the simulation, basically. There's a lot of hysteresis in the process. And in fact, if you initialize a simulation from an aggregated state, even in conditions where it might not organize on its own, it's quite happy to stay organized. And so you have to do a lot to break it up. The easiest way to break it up is to put in vertical wind shear into the simulation, because that's going to start causing mixing between these moist and dry regions. So anything that gives you that might break it up, but otherwise it's just so And the areas outside the convective cluster, it's so unfavorable to convection there that it just stays its own little happy environment.
Very last question.
Joe Harrington, University of Central Florida. Welcome to Florida.
Where are you? Oh, there you go.
So this is another step back question. The more I hear about short-term processes like convection and waves and so forth, the more I'm convinced that they're critically important to long-term processes. And I just wanted to ask, and I know this is a very naive question, but how do you connect processes like this to, say, a climate model that's going to run for 1 billion years?
That's a good question. I mean, I think the connection is through how these smaller scale processes kind of rectify on the larger scale, like I was talking about towards the end with these impacts on the larger scale climate. I mean, if the atmosphere, was totally the same, regardless of whether convection was in a cluster or a line or a circle or a star or whatever, then maybe those small scale processes wouldn't matter for 1 billion year simulation. But if any process sort of has an impact that persists over a longer time period than its lifetime, or on a larger scale of it, then it's something that would be relevant over those long scales. From a kind of more fundamental perspective, convection itself, it's setting the structure of the temperature profiles in the atmosphere. I mean, the reason, that we have the surface temperature that we do and the rate of decrease with temperature with height, that's because of these small scale hour-long, time period convection things. And so that's, the strongest example for how these small scale processes are something that we have to take into account. So, that's why climate models where they're parameterizing these things have to work so hard to get those things right. Because those small scale processes do play a big role. When we're talking about, kind of centennial scale future climate projections, the biggest uncertainty in those is how these convective clouds are handled because of some of these regions. Longer scales, billions of years, I mean, again, that's where you start having other things like, geologic processes and carbon cycles starting to become really important. But, we still need to know what the temperature structure is, and convection is going to tell us that. So, yeah.
So let's thanks again.